In the last few lectures, we had discussed diffusion, which is the transport of mass, momentum or energy due to the molecular fluctuating velocity. In this, we will start discussion on dispersion, which is the transport due to the fluid fluctuating velocity. Initially, we had made a distinction between two mechanisms of transport. One is convection, which is transport of material along with the fluid, and the other is diffusion due to the molecular velocity fluctuations. Now, convection can further be separated into two processes in flows where there are large instantaneous velocity fluctuations either spatially or in time. Okay. And we are considering we make a distinction between the mean velocity and the fluctuations relative to the mean velocity. Okay. An example is a turbulent flow, okay, which we had already seen. If we take the flow in a pipe, for example, okay, if we take the turbulent flow in a pipe, for example, we know that for a turbulent flow, okay, we know that for a turbulent flow, the velocity profile is more plug like with a larger gradient at the walls and a smaller curvature at the center in comparison to a laminar flow. Okay. And there are large instantaneous velocity fluctuations in all directions in a pipe flow. Okay. There are large instantaneous velocity fluctuations in all directions at each point. Okay. So, the average velocity at a point is defined as, okay, the average velocity in this case would be a time average. Okay. If you actually take the, if you actually plot the velocity at a point, okay, if you plot the velocity at a point, okay, the three components of the velocity say, okay, Vx versus time, Vy versus time, and the third component Vz versus time. Okay. Vx will fluctuate around a non-zero value, okay, whereas Vy and Vz are 0 on average. Okay. So, they will have fluctuations about 0. Okay. So, each of these components, they will have some mean value, which I will call Vx this mean value, which I will label as Vx bar, okay, and there is a fluctuations about that, okay, instantaneous fluctuations. In a turbulent flow, these fluctuations are comparable to the mean value. How do I define the mean value? Vx bar, I take it as 1 over an averaging time times integral 0 to t average dt times Vx. Okay, that is, I take the integral of Vx with respect to time for a time period t averaging TAV, and I divide by TAV to get the mean velocity. Of course, the averaging time has to be much larger than the time characteristic time of the fluctuations in the velocity. Okay. Only then will I get a statistical average, only if the averaging time is much longer than the time of characteristic time of fluctuations of the velocity. Okay. And if I take Vy and Vz average, both of these will be 0, because at that particular location the flow is on average in the x direction. There is no average flow perpendicular to the flow direction. Okay. And because of that, the average of Vy and the average of Vz will both be 0. Okay. And then you can define the fluctuating velocity. Vx prime is equal to Vx of t minus the Vx bar average. Okay. The fluctuating instantaneous fluctuating velocity is Vx of t minus the average value. Fluctuating velocity in the y direction is just equal to Vy of t because the average is 0, and similarly in the z direction. Okay. So, this is the decomposition into the the average velocity and the fluctuating velocity. Now, the transport of mass, momentum or energy due to the average velocity is the convection due to the average velocity, okay, the average convection. Okay. However, the fluctuations can also transport mass, momentum or energy. Okay. The transport of mass, momentum and energy due to the fluctuating velocity, which is 0 on average, are referred to as dispersion. Okay. So, when you artificially separate out the fluid velocity field into an average value, a mean value, in a turbulent flow this is the time average. So, you artificially separate it out into an average value and fluctuations about that average. The transport due to the average value is the convection due to with the mean flow. Okay. The mean flow convection is the convection due to that average value. The convection due to fluctuations is the dispersion. Okay. That is what is referred to as dispersion. So, let us examine that in a little more detail. Okay. Now, these fluctuations, so if I had for example variations in temperature or variations in concentration between the wall temperature and the average fluid temperature, then these fluctuations will also cause fluctuations at a location in the temperature field or the concentration field. Okay. Okay. So, they will also cause fluctuations in the temperature or the concentration field, okay, at that location, and these are fluctuations in the fluid temperature or the fluid concentration. Okay. So, the temperature and concentration can also be expressed as an average and a fluctuating value. So, for example, the average concentration, okay, C bar, okay, at some location, okay, I write it as 1 over T average integral 0 to T average dt times C. Okay. The average temperature is equal to 1 over T average integral 0 to T dt times the temperature. Okay. This temperature at that location is a function of time. Okay. So, I can write the average value of the concentration or temperature at that location and the average value of the velocities at that location. And corresponding to that, I can define the fluctuating concentration as a function of time minus the average concentration, fluctuating temperature as a function of time minus the average temperature. Okay. So, these are the quantities. Now, let us examine what is the flux at a point, okay, in the x direction, say. Okay. I will take the concentration flux, okay, the mass flux, okay, at a location. Okay. So, at the same location I will take the mass flux in the z direction. Okay. That mass flux is equal to in the I am sorry I will take the mass flux in the x direction. Okay, the mass flux in the x direction is equal to the normal velocity, okay, that is the velocity in the x direction times the concentration, okay, is equal to Vx into C at that location, okay, the product of the velocity and the concentration. I can define an average flux at this location. Okay. The average flux at this location is equal to 1 over TAV, it is exactly the same definition, integral 0 to TAV. Vx times the concentration. This is the definition of the average flux in the x direction at a location. Now, for these I can substitute for the velocity and the concentration using this relation. Okay. I can substitute for the velocity and the concentration, express it as the sum of a mean value, a time averaged value plus a fluctuation. Okay. So, this is equal to 1 over the averaging time integral 0 to T A V dt into Vx bar plus Vx prime of t into C bar plus C prime of t. That is the expression for the flux at a location. Okay. And you can see that this contains 4 parts. Vx bar C bar plus Vx bar C prime plus Vx prime C bar plus Vx prime C prime. Okay. Just expanding this out. Note that Vx bar and C bar are independent of time. Okay. They are already averaged over time. Okay. So, for example, the first term Vx bar and C bar are independent of time, right. So, I will just get the average as the value itself. Okay. Okay, because they are independent of time, the average will be equal to the value itself. Okay. The second term Vx bar is independent of time and 1 over T average integral 0 to T average C prime. Okay, because Vx bar is independent of time, whereas C prime depends upon time. Okay. The third term will be C bar is independent of time. One over T average integral 0 to T average dt times Vx prime. Okay. And the last term is integral dt Vx prime C prime. Okay. So, those are the 4 terms. Integral of C prime from 0 to T average 1 over T average has to be 0, because that is the integral of a fluctuation. Okay. You can easily verify this, because integral of C, for example, is equal to C bar. Okay. So, the integral of C minus C bar, the integral of C minus C bar has to be equal to 0. Okay. Whenever you have a term that is linear in the fluctuating component, it will average out to 0. Okay. So, this is linear in the fluctuating component, it averages out to 0. This is also linear in the fluctuating component, it also averages out to 0. Okay. The last term on the right does not average out to 0 in general. Okay. Vx bar C plus this is the average, time average of Vx prime times C prime. Okay. And this does not in general average out to 0. Okay. This does not in general average out to 0. Okay. The reason is because the velocity and the concentration fluctuations could be correlated in general. Okay. The product of the velocity and concentration fluctuations does not have to be 0, okay, in general. These could be correlated. Okay. So, to illustrate that, let me just consider some concentration fluctuation time and some velocity fluctuation time. Okay. Each of these on average is equal to 0. Okay. Each of these on average is equal to 0. Okay. However, the product of two terms which average to 0 does not necessarily have to average to 0. Okay. For example, if Vx prime is proportional to C prime, even though both of them average to 0, you get the square of a number Okay, even though a number, right, C prime could be positive or negative, if Vx prime and C prime are proportional to each other, you get a square of a number which is always positive. So, the product of those two in general does not have to average out to 0. Okay. Okay. It could in general be just positive, or it could average out to a positive or a negative value, okay, depending upon whether these two fluctuations are correlated or anti-correlated. Okay. If they are correlated, so that one function is more often positive when the other one is positive, you will get a positive value. If they are anti-correlated, you will get a negative value. Okay. So, because of that, you get a contribution to the flux due to the fluctuations. Okay. So, this first term is the convection due to the mean flow, the mean velocity times the concentration at that location. That is the convection due to the mean flow. The second term is the dispersion. It is due to fluid convection, but due to the fluid velocity fluctuations. The correlation between the fluid velocity fluctuations for the correlation between the fluid velocity fluctuations and the concentration fluctuations could result in transport, okay, could result in a non-zero flux, even though the velocity fluctuations and the concentration fluctuations both are on average 0. Okay. And this is what is called the dispersion flux, or it is also called as the Reynolds flux. Okay. It's called the Reynolds flux. Okay. And recall that when we did kinetic theory of gases, we said that the motion, the flux in one direction is due to the root mean square velocity times the concentration of that molecule at a location about one mean free path away from the surface. In a similar manner, the Reynolds flux is also the product of the fluid velocity fluctuations, not the molecular velocity fluctuations, the fluid velocity fluctuations and the fluid concentration fluctuations averaged over time. Okay. That is the Reynolds flux in the x direction. The Reynolds flux in the y direction is equal to Vy prime C prime average, and that in the z direction is equal to Vz prime C prime average. Okay. So these are the Reynolds fluxes in the three directions. Okay. And in a similar manner, you could have thermal fluxes as well. Okay. The temperature flux is going to be the Reynolds flux for temperature is going to be equal to Qx average, for example, will be equal to the fluid velocity fluctuations times the thermal energy fluctuations. Okay. So, the fluid velocity fluctuations times rho Cp thermal energy fluctuations. Okay. And since rho and Cp are constants, this becomes equal to rho Cp times the correlation between the fluid velocity fluctuations and the temperature fluctuations. The average of the product of the fluid velocity and the temperature instantaneous values. Okay. That is the Reynolds flux for heat. And the Reynolds flux stress for momentum, okay, that is equal to the momentum density fluctuations times the fluid velocity fluctuations. Okay. In this particular case, note that x is the direction of momentum, z is the direction of transport. Okay. In this case, x is the direction of momentum, z is the direction of transport. Okay. Therefore, I have to take the direction of transport as the z direction for the fluid fluctuating velocity. This is the direction of transport times the momentum in the x direction. Okay. That average. Okay. That is the Reynolds stress, okay, due to the fluid velocity fluctuations. And I had explained in the last class that for the stress alone, right, you have a negative sign because the stress is positive when the momentum of the volume below increases, if you consider the plus z direction as in the upward direction. Okay. So, for that reason you have to have a negative sign here. Okay. So, this is equal to minus rho V x prime V z prime average if the density is a constant, as it is for the incompressible fluids that we will consider here. Okay. So, let us solve a specific problem to illustrate how this works. Okay. So, if you consider, okay, the fluctuations in concentration and velocity at a point. We will just consider a single frequency variation. C is equal to the fluctuating concentration C 0 prime sine of omega t, okay, and the velocity V x prime, okay, is equal to V x 0 prime sine of omega t plus some phase angle phi, okay, where t is the time and omega is the frequency. Okay. So, we are basically considering a single frequency variation, okay, in velocity, in concentration and in velocity. Okay. So, this will be C prime, this will be V x prime. Okay. It is varying with a single frequency omega. Now, in this case the concentration average, okay, the average of that is defined as 1 over TAV integral 0 to TAV dt times C naught sine of omega t. Okay. And I said that the averaging time has to be much longer than the characteristic time scale for variation of the concentration. Okay. The characteristic time scale for variation of the concentration is in this case the time period, which is equal to 2 pi by omega. Okay. Okay, the characteristic time for variation of the concentration is 2 pi by the frequency. Okay. So, therefore, I require that the ratio of the averaging time by 2 pi by omega has to be much larger than 1. That is, the averaging time has to be much longer than the characteristic time for variation of the concentration, okay, or this corresponding to omega t average, okay, has to be much greater than 1. Okay. So, that is the condition on the averaging time. There is a factor of 2 pi there, but we can just include it in a constant. Okay. So, that is a condition for the averaging time. Okay. So, with that condition, let us evaluate this. Okay. So, this is equal to 1 over TAV into minus C naught cos of omega t by omega between 0 and TAV. Note that this is proportional to 1 over omega times TAV, okay, and the condition on the averaging time was that this has to be much larger than 1. Okay. So, in the limit as omega TAV becomes large, this is equal to 0. Okay. In the limit as omega TAV becomes large, this is equal to 0. As expected, the average of the fluctuating concentration is equal to 0. Okay. And you can do a similar calculation for the average of the fluctuating velocity also. and you can easily verify that that is also equal to 0. Okay. So, both the concentration fluctuation and the velocity fluctuation, both of these average out to 0. What about the Reynolds flux? Okay. J x r average is equal to 1 over TAV integral 0 to TAV dt of C naught C naught prime Vx naught prime sine of omega t sine of omega t plus phi. Okay. So, it is a product of the concentration fluctuations and the velocity fluctuations. Velocity fluctuations shifted by a phase angle phi with respect to the concentration fluctuations. Okay. Now, I can simplify this using the expansion formula for sine functions. Into sine omega t cos phi plus cos omega t sine phi. Okay. Okay, using the expansion formula for sine functions. So, this is equal to sine square omega t cos phi plus sine of omega t cos of omega t sine phi. Okay. And now I can express this in terms of sine square omega t can be expressed in terms of sine of 2 omega t. Okay. So, this is equal to half into 1 minus cos of 2 omega t into cos phi plus sin omega t cos omega t is sin 2 omega t by 2. Okay. So, I get half sin of 2 omega t sin phi. Okay. These use basic fundamental trigonometric relations for calculating the expansion. Okay. So, if I do that, I will get C naught prime Vx naught prime by T average integral 0 to T average dt half of 1 minus cos of 2 omega t times cos phi plus half of sine of 2 omega t sin phi. And I can do this average this integral quite easily. I will get C naught prime Vx naught prime by T average into T by 2 minus minus sine of 2 omega t by 2 omega into cos phi minus half into cos of 2 omega t by 2 omega sin phi. Okay. This evaluated between 0 and T average. I get here a T average by 2 minus cos phi minus sin 2 omega t by 2 omega cos phi minus cos of 2 omega t by 2 omega sin phi. Okay. These evaluated between 0 and t average, and this between 0 and t average. Okay. The first term which I had here, which was 1, became a t, and that between 0 and t average is just t average. Now, you can see here that both of these terms here, okay, both of these terms, okay, when multiplied by 1 over t average, okay, have to go to 0 because omega times t average is going to infinity, okay, as we had seen over here. Okay. So, both of these terms do decrease to 0. Okay. However, this first term does not. Okay. This first term does not decrease to 0, okay, because it has a t average in the numerator and a t average in the denominator. Okay. And therefore, in the limit as t average becomes large, this term goes to a finite value, and that is C naught V x naught prime, okay, times cos phi by 2. Okay. Okay. So, the t average and t average in the numerator and denominator of this term will cancel out, and I will just get C naught V x naught prime by 2 into cos phi. So, that is the Reynolds flux for this particular case. Even though C prime and V x prime both have 0 mean values, the product when integrated over time does not have a 0 mean value, it has a non-zero value, and that is because these two are correlated. Okay. It is proportional to cos phi, where phi is the phase shift. Okay. And because of that, this is the dispersion flux. The correlation in the velocity and the concentrations result in a net non-zero transport, even though on average the velocity and the concentration fluctuations are 0 on average. The net flux, which is proportional to the product of the two, is non-zero on average. Okay. And this results in a non-zero value of the transport of mass in this particular direction. The Reynolds flux is non-zero because the velocity and the concentration are correlated in this case. So, this is just a simple illustration of how you can get a non-zero flux, even though the fluctuation velocity and concentration average out to 0. I will continue this a little bit in the next lecture, and then I will complete by considering dispersion in a packed bed and Taylor dispersion, and then we will go on to unidirectional transport. I will see you in the next lecture.